Welcome back to the deep dive. It's great to have you with us again as we explore these really complex challenges where, technology and methodology collide. Our goal, as always, is to cut through the jargon, get past the hype, and really give you the core insights you need.
It's good to be here. And today we're tackling something that is, I think, incredibly high stakes. It's all about securing and scaling transcription for very sensitive research data.
Right. And if you, our listener, are involved in cognitive studies, clinical trials, maybe social science focus groups, really any field that deals with recorded human speech, you know this already. Transcription it's not some simple admin task.
No, not at all. It's really the bedrock of your entire analysis.
That's so true. The quality of that initial transcription, I mean, how accurate is it? How reliably does it capture who is speaking? And maybe most critically, does the data itself stay secure and private? All of that really determines the validity of your entire study.
And it's ethical compliance, which is huge.
Absolutely. So we've been immersing ourselves in some fascinating source material that describes a production-ready open source workflow. And this system was engineered from the ground up to operate securely inside these massive institutional high-performance computing environments. You'll often hear that called HPC.
Yeah, and our mission for this deep dive is to really unpack what that means. We're going to clearly define the technological requirements for true methodological rigor. We'll start by dissecting why just relying on consumer-grade cloud transcription tools, even the ones using the best AI, is often just fundamentally incompatible with serious research ethics.
And then after we've established the problem, we're going to take a really detailed look at the sophisticated engineering that's required to achieve what's called complete data sovereignty.
Right. And to deliver that production-grade quality control, all while operating entirely offline, which is the key.
Okay, so let's unpack all of that. I think we have to start with the engine that really makes any of this possible in the first place. There's been this huge paradigm shift in automated speech recognition technology just over the last few years.
Oh, it's staggering when you look back. Just staggering how quickly speech-to-text systems have evolved. For years, I mean, for decades, transcription was dominated by these proprietary systems that needed massive domain-specific training.
Or you were stuck with that clunky, super error-prone dictation software.
Exactly. The transformation we've seen, which has been driven by generative AI, has been profound, really profound.
The centerpiece of that whole transformation, the technological disruptor, really, that changed everyone's expectations of what ASR systems could do, is the Whisper model family from OpenAI.
Precisely. The release of Whisper was a genuine moment of democratization for state-of-the-art automatic speech recognition. And it's not just, another small incremental improvement. It's a foundational change. And that's because of the sheer scale and the diversity of its training data.
Can we just dwell on that for a second? Because that number, 680,000 hours of multilingual audio data, that's just an astonishing number. It's so important to understand why that makes the model so robust.
It is. I mean, think about what that really means. It means the model hasn't just heard, pristine, clean studio recordings. It has learned to recognize speech patterns, accents, background noise, different acoustics, complex linguistic structures.
Across dozens and dozens of languages.
Right. It represents a real paradigm shift toward a generalizable, highly robust system, one that can handle the messiness of real-world audio.
Like a focus group that was recorded with a slightly dodgy microphone in a noisy university conference room.
Exactly that scenario. And it can handle that without requiring researchers to spend months fine-tuning it. So it's very quickly become the sort of unquestioned gold standard for general transcription tasks, and it often outperforms older, highly proprietary solutions.
Okay, so if we accept that Whisper is the gold standard for accuracy, then the immediate question for any researcher listening is, why can't I just use a convenient chat interface, like ChatGPT or Google Gemini? We know they use these powerful models internally. Why do we need this massive, complicated institutional engineering effort?
And that is the absolute crux of the problem. This is where that consumer-facing convenience completely breaks down when it's faced with academic and ethical rigor.
Right.
While those chatbot interfaces are fantastic for personal use, transcribing a quick voice note or summarizing a short meeting, for serious production or research workflows, they introduce three, I would say, non-negotiable limitations.
Okay, let's define those three limitations very clearly. And let's start with the most basic technical hurdle that just stops a research team dead in its tracks: file size.
Limitation number one, file size constraints. It's as simple as that. If you look at the technical specs of most of these chatbot interfaces, they impose really strict upload limits. Almost always, they're going to cap your audio recordings at 25 megabytes or less.
And what does 25 megabytes actually mean in the real world in the context of typical research data?
It translates to roughly only 20 to 30 minutes of standard quality audio. That's it. So if you're conducting a qualitative study, standard methodology often requires you to do these in-depth interviews or focus groups that can regularly span.
60 minutes, 90 minutes, even 2 hours.
Easily. So that means a single 2-hour interview has to be manually chopped into maybe 4 or 5 separate segments just to fit into this arbitrary upload window.
Which is just, it's not just tedious.
It's incredibly tedious. It requires hours of just prep work, segmenting files, renaming them. But more than that, it introduces a methodological risk. You're interrupting the natural flow of the conversation, and then you have to rely on stitching these files back together perfectly.
Which just adds unnecessary complexity and, potential for errors right into your data pipeline from the start.
It just makes transcribing any kind of high-volume, lengthy research sessions totally impractical.
Okay, so that's the practical problem. But moving beyond the sheer inconvenience, we hit the second, and I would argue far more damaging, problem for the scientific method, the lack of reproducibility.
Yeah, this is where we zoom out to the bigger picture. We're talking about methodological integrity, academic publication standards. And here, the, the opacity of these cloud-based solutions is a critical weakness.
A black box, essentially.
A total black box. When you use a commercial API or a chatbot for transcription, you have no visibility into several key factors.
And these are the exact factors that, an internal review board or a journal editor would absolutely ask you about, right?
Absolutely. First, you can't see the exact model versions being used. Did they use Whisper Large V2 or was it Large V3? They're different. You don't know the specific processing parameters, things like beam size or temperature settings, which really do influence the final output.
And crucially, you have no idea what post-processing steps they might be applying behind the scenes.
None. Things like normalizing punctuation, correcting formatting, even their own internal quality checks. It's all hidden from you.
So for me as a researcher, this lack of transparency is devastating because if that cloud provider decides to update their underlying model or they change their rules between my session A and my session B, I have no way to verify or replicate the exact results.
Precisely. And reproducibility is the cornerstone of science. If your transcription is handled by a system whose parameters you can't control or even record, you simply cannot defend your methodology robustly. You can't replicate your own findings. It's why academic institutions really can't responsibly recommend these tools for high-stakes data analysis.
Which leads us directly to the elephant in the room when we're dealing with human subjects.
Yeah.
Privacy and compliance risks.
This is the definitive constraint. There's no getting around this one, especially in research fields that touch on health, sensitive personal beliefs, or vulnerable populations. Transmitting confidential, sensitive audio data to external third-party servers. Even under the most stringent contractual terms, it's very often a non-starter.
Because institutional policies like those from research ethics boards or IRBs, they are just extremely strict about data transmission.
They have to be. The risk of violating major data protection regulations like the GDPR in Europe or institutional-specific mandates about patient confidentiality, it's just too high.
Even if a cloud platform promises, temporary storage or offers one of those so-called temporary chat modes.
Even then, the very act of transferring that raw, sensitive audio data across the open internet to a non-institutional server introduces a risk that most compliance officers and researchers simply cannot and will not accept.
Okay, so we firmly established that the cloud is too restrictive, it's too opaque, and it is far too risky for sensitive data. This forces us into the second major section of our deep dive, the sophisticated engineering that's required to bring this powerful AI model itself inside the controlled environment.
And that is the core solution. You see, the need for a local workflow isn't just a preference, it's a necessary form of data governance. We have to solve all three of those problems we just talked about: risk, scale, and reproducibility, all at the same time.
So let's start with the most immediate and critical benefit of building a local system: achieving complete data sovereignty. What does that actually mean in practical terms for a researcher?
Complete data sovereignty means that the system ensures your sensitive audio content never, and I mean under any circumstances, leaves your controlled institutional environment. It achieves this by completely eliminating the cloud's primary moment of risk, which is transmission.
So how is that risk of transmission actually eliminated?
Well, the sources we looked at explain that the pre-trained models, and specifically we're talking about the optimized Whisper Large V3, sourced from reputable places like Hugging Face, they are downloaded once by the institutional IT team,
Just one time.
one time into the secure environment. After that initial download, all subsequent transcription execution runs entirely offline. You could unplug the internet cable. We're talking about an air-gapped system where the transcription process itself is completely self-contained.
That is the magic bullet for compliance, isn't it? If the audio file never hits a third-party server, you fully satisfy those stringent GDPR requirements and all the institutional data policies.
Absolutely. This approach fundamentally shifts control. Instead of trusting an external vendor's security promises, the institution relies on its own established and auditable security perimeter.
Hmm.
It fully meets the ethical and regulatory demands that are so common in academic research and in healthcare.
So once you're running locally, you don't just gain security, you also shatter those arbitrary size limits that plagued the cloud services. And this brings us to the next huge challenge, achieving unlimited scale through high-performance computing integration.
And the contrast here is just dramatic. We go from those arbitrary 25 megabyte caps to the capability of handling audio files of any length. Not just that, but executing massive, large-scale batch operations. This capacity is entirely enabled by designing the system specifically for these HPC environments.
So tell us more about the engineering behind that scale. What does it actually take to get an AI model like this and make it, sing on an HPC cluster?
It's all about parallelism and resource management. This particular system is designed to leverage graphics processing units, or GPU acceleration, because GPUs are the key to massive high-speed neural network processing, and it uses the industry standard management tool for large academic clusters, which is the SLURM job scheduler.
SLURM. It stands for Simple Linux Utility for Resource Management. For listeners who might be less familiar with HPC, what is SLURM actually doing in this context? How does it manage that kind of scale?
Think of SLURM as the highly intelligent traffic controller for the entire computing cluster. When you have hundreds or even thousands of researchers all trying to run demanding computations at the same time on a shared resource, SLURM prevents chaos.
Okay.
And for this transcription workflow, it's what enables that unlimited scale through parallel processing.
So let's take a real world example. A research team has, say, 500 hours of focus group audio they need transcribed by Monday.
Okay. The system uses what are called submission scripts that provide dynamic job array sizing. So what that means is the system looks at those 500 files, it calculates the processing time and the resources needed, and it automatically matches the number of simultaneous processing jobs to the number of input files.
So it's orchestrating everything.
It orchestrates the execution across multiple GPU nodes at the same time. It's true high-throughput batch processing.
That is the kind of intelligence that saves countless human hours and makes these really ambitious, large-scale qualitative studies actually feasible.
And crucially, the system is also intelligently optimizing how it uses those resources. It will always prioritize GPU allocation because that's where you get the massive speed up, but it also includes a graceful fallback mechanism.
What does that mean, a graceful fallback?
It means if all the GPU queues on the cluster are completely saturated, or maybe a specific audio file is just too complex for the available GPU memory, the job doesn't fail. It can fall back to running on the CPU instead.
Slower, but it gets done.
Slower, but it ensures continuous operation and prevents the job from just crashing.
That dual path approach, prioritize speed with the GPU, but guarantee completion with the CPU, that really is a hallmark of production grade stability, isn't it?
It really is. And on top of that, the system doesn't force this one-size-fits-all approach. Researchers can customize the resource limits for their specific job using standard HPC commands, things like memory and time limit. This kind of flexibility is absolutely essential for managing the sheer scale and variety of data processing that happens in a big institutional environment.
Okay, so we've got security, we've got scale. Let's return to that third methodological requirement that was completely broken by the cloud. Reproducibility. We need to be able to trust the environment itself.
Transparency is the operational mandate here. Unlike that opaque black box of the cloud, in this local workflow, every single aspect of the processing pipeline, the specific model you select, the audio enhancement parameters, the text processing rules, it's all configurable, it's documented, and it's exposed through command line options.
Now, researchers can keep a meticulous record of their methodology, which they can then cite directly in their publication.
Exactly. But you've hit on a key point. That sounds simple, but maintaining stability and reproducibility in a shared massive computing cluster, which is constantly being updated and patched. That is notoriously difficult. Specifically, dealing with Python dependencies and environments is usually a complete nightmare.
It's the bane of every data scientist's existence.
It really is. That's, challenge number 5 in the technical architecture. And the meticulous solution that is provided here is a key insight for anyone running large-scale data pipelines. Running these complex Python environments with deep, interlinked dependencies like PyTorch across different HPC module systems is a source of constant frustration.
So how does the system ensure stability across all these different institutional setups that might be using different Linux distributions or different module systems?
It all comes down to meticulous version control, often called version pinning. So while it recommends using Python 3.12, it includes critical support for 3.11. But more importantly, it specifies exact version pinning for those complex dependencies. For example, the sources specify needing PyTorch version 2.5.1 plus CPU.
Why is that specific version so important? Why can't a researcher just grab the newest version, say 2.7 or 2.8?
This is one of those deep technical details that makes all the difference for stability, especially for non-GPU processing. The developers explicitly advise against newer versions, like PyTorch 2.7 on CPU-only systems because of known ABI compatibility issues.
ABI being the application binary interface.
Right. So if a researcher just installed the newest version, their jobs might silently fail or produce unpredictable results because of these very subtle clashes in how the compiled code interacts with the underlying operating system.
So, by enforcing this really precise version control, which is managed through platform agnostic setup scripts, the engineers are basically taking all the guesswork out of the environment setup for the researcher.
That's the goal.
They're ensuring that the system works reliably, regardless of when or where it's run on the cluster. And that is fundamental trust built right into the pipeline.
It is. It ensures that the researcher is spending their grant money on scientific analysis, not troubleshooting software installations. Stability and reproducibility are secured through these very meticulous, unglamorous technical decisions, like specifying exactly PyTorch 2.5.1.
Okay, so we've covered the security and the infrastructure challenges. Now let's transition into the linguistic engineering part. Because even with the best, most stable environment, Gen AI models like Whisper can still introduce specific artifacts that need to be cleaned up before a transcript is truly usable for qualitative analysis.
This is where advanced quality control moves beyond just basic transcription and into what you could call intelligent post-processing. The raw output from even a great model like Whisper isn't always clean enough for publication or for rigorous data coding.
So let's talk about the first and maybe the most common AI artifact. It's called spurious repetitions. Can you define that for us?
Spurious repetitions are a form of AI hallucination. It's where the generative model essentially gets caught in a loop and it starts repeating phrases or short segments of text unnecessarily. For instance, a transcript might read, "We believe the outcome was beneficial, we believe the outcome was beneficial, we believe the outcome was beneficial," and then we stopped.
That repetition is obviously not natural human speech. It's an artifact of the model.
Clearly. The challenge then is making sure your cleaning process doesn't accidentally delete intentional repetition or human stuttering or phrases someone might use for natural emphasis. How do you solve that without just using a simple blunt filtering tool?
Right.
The solution here is quite sophisticated. It's activated by a command line flag, fixed spurious repetitions, and it employs an algorithm that goes far beyond just looking for simple, immediate duplication. It engages in a kind of linguistic analysis. It considers the frequency, the context within the surrounding dialogue, and the structural pattern of the repeated segments.
So it's actively looking for patterns that scream machine error versus patterns that just sound like natural human language quirks.
Exactly that. It's designed to differentiate between, for example, the data was significant, a clear artifact. And I, I really feel that the answer is yes, which is just a human hesitation or a stutter. This intelligent distinction ensures the cleaning process improves the transcript's usability without destroying the authenticity of the captured human speech.
And that authenticity is paramount for qualitative coding.
Absolutely.
Okay, another common quirk, and this is especially true because Whisper is so multilingual, is the erroneous language switch.
Right. You have to remember, Whisper was trained on 680,000 hours of multilingual data. Now, this is mostly a huge strength, but one of the weaknesses is that when it encounters phonetically ambiguous sounds, or maybe a speaker with a very heavy regional accent, it can sometimes erroneously decide that the speaker has switched languages.
And it might just insert some random French or Spanish text right in the middle of an English sentence.
Exactly, which completely destroys the flow and the meaning.
So how is that addressed in the local workflow?
It's a very simple but highly effective fix. Just constrain it. Researchers can use the language argument to constrain the model to a designated language, say English. By telling the system, hey, assume this entire recording is only in English, you prevent those unwanted artifactual language switches. It massively improves the methodological consistency of the final output.
All right, now we need to move to what is arguably the most critical quality control feature for any sensitive human research: intelligent privacy protection through personal name masking.
This is such a nuanced challenge. It really embodies the trade-off that's inherent in all data processing. The goal is clear. You want to reliably identify and replace sensitive personal names to protect participant anonymity. The difficulty lies in avoiding the false positives.
Meaning you can't have the system masking common conversational words or technical terms or geographical locations that just happen to sound like a name.
Precisely. Can you give us an example of a problematic false positive?
Sure. If the model masks the word may when a participant says, I have a meeting scheduled in May, or if it masks the word Jordan when the discussion is about the country, not a person, or the name white when they're talking about a color.
The analyst loses crucial context, and the conversation flow is completely disrupted. A simplistic name filter is worse than useless.
So how does this system manage that incredible complexity, that balance between protecting identity and maintaining the semantic integrity of the transcript?
It uses a really clever, multi-tiered solution that actually forces the researcher to explicitly define their tolerance for risk and for coverage.
Let's break that down. Let's start with Tier 1, the default setting.
Tier 1 gives you high security with a very low risk of false positives. It relies on a carefully curated, smaller database of just over 1,700 names across 9 languages. This list was specifically refined by the developers to minimize the masking of common conversational words. It's the safety-first default option.
But I can see how some research, especially large-scale social science datasets, might need much broader coverage for more diverse names.
And that brings us to Tier 2, optional maximum coverage. Users can choose to enable vastly broader databases, like the comprehensive Facebook First Names database, which has around 730,000 names, and a surnames database with nearly 1 million names.
Wow, that sounds incredibly powerful, but also incredibly risky.
It is, and it's a deliberate risk-reward calculation the researcher has to make. The system documentation is very clear. It states that while this vastly increases the potential coverage of less common names, the researcher must accept that it also significantly increases the risk of false positives.
So it puts the control and the ultimate ethical responsibility back onto the research team.
Exactly where it belongs. And the researcher still retains the final granular control over the whole masking process.
Which is absolutely essential.
It's the final safety net. Researchers can provide custom lists of names they want the system to exclude from masking. For instance, if they're talking about public figures, specific research team members, or common location names, they can also manually exclude common English words that might be problematic in their specific domain.
And the final output is then anonymized, replacing those detected names with placeholders like name 1 or name 2.
Right, which protects privacy while keeping the conversation flow totally intact for coding and analysis.
Okay, so moving beyond the text itself, the system also anticipates the challenges of poor quality input audio. This is so crucial for real-world research.
That's where the optional audio enhancement pipeline comes in. This is a crucial pre-processing stage, designed specifically for challenging acoustic conditions, things like high background noise, reverberation, or just inconsistent speaker volumes.
What does that pipeline actually do to the audio?
You can think of it as a sophisticated audio engineer that's built right into the transcription tool. When you enable it, it applies a combination of spectral noise reduction, which intelligently targets things like an air conditioning hum or fan noise.
Okay.
Dynamic range compression, which ensures that the softest speaker and the loudest speaker are equally audible, and signal amplification.
And I understand the enhancement process is also adaptive, which feels like a major engineering upgrade over just a simple blanket filter.
It is adaptive, and that's critical because every interview environment is different. The process uses the first half second of each recording as a noise reference. By analyzing that tiny initial segment, it can dynamically adjust the enhancement parameters to the specific acoustic profile of that particular recording.
So it ensures optimal clarity without introducing a bunch of new processing artifacts.
That's the idea.
Okay, so once the transcription is done and it's all cleaned up, the final essential quality feature, especially for qualitative analysis, is knowing who said what. That's speaker diarisation.
Speaker attribution is absolutely non-negotiable for research that relies on conversational turn-taking or quantifying contributions from different people. The system integrates a tool called piano.audio, which is widely regarded as a best-in-class, open-source tool for speaker diarisation. You just enable it with the speaker attribution flag.
And it goes through and identifies the different voices, tagging the transcript with speaker one, speaker two, and so on, which transforms a big monologue block of text into a structured dialogue that's ready for coding.
Correct. It transforms that raw text into usable social data. But there is a small, practical, technical requirement here. Since Piano.audio relies on very specific, highly accurate models that are hosted on Hugging Face, enabling this advanced functionality requires the user to have a Hugging Face user access token.
A necessary step to access that level of specialized model performance.
It is.
And then to complete this whole picture of methodological rigor, the system also has to provide flexible output and comprehensive auditability.
Yes, and it delivers dual output formats, which is key for any mixed methods research environment. You get the raw plain text transcript, which is ideal for programmatic analysis and archiving, but you also get a nicely formatted Microsoft Word document, which is often what qualitative coders prefer for easy editing and sharing.
And crucially,
Crucially, the system generates comprehensive processing metadata and timestamps. This supports both immediate reproducibility and long-term audit purposes, satisfying all those institutional archiving requirements.
so we've walked through the what all the features, the why compliance and rigor, and the how the HPC integration. Let's finish up by looking at the architectural choice that underpins all this stability and future proofing.
The architectural decision here is highly pragmatic. The entire system is implemented as a monolithic Python script, just one file, transcription.py. And this single script integrates all the core components, the Whisper model loading, the audio preprocessing, the name masking, the diarisation, all into one unified processing engine.
You know, in a world that is constantly pushing for microservices and distributed computing, a monolithic script might sound a bit outdated. But in this specific institutional context, it really feels like an intentional design choice for stability.
Oh, it's entirely intentional. The rationale prioritizes simplicity, maintainability, and ease of deployment. For compliance officers and IT teams who are managing highly sensitive data, having a single auditable point of control, one script, is far simpler and safer than trying to verify the integrity of a complex distributed microservices environment. It orchestrates the entire multi-stage pipeline reliably, all through one unified command line interface.
And this architecture is what guarantees the long-term sustainability of the research, which is a massive concern for any grant-funded project.
Absolutely. This design choice isn't just about security today, it's about future-proofing the methodology. While the system is optimized for OpenAI's Whisper Large v3, the architecture is designed to support any Hugging Face-compatible ASR model.
Which means a multi-year, multi-million-dollar study isn't suddenly derailed if a cloud provider retires an underlying model, or if a new specialized model for, say, clinical speech emerges.
Precisely. Researchers can easily swap in specialized ASR models for domain-specific applications without having to rebuild their entire secure, local, HPC integrated infrastructure. This modularity ensures that the investment in local security and stability pays dividends for years to come.
And this is where we circle back to you, the researcher planning your next study. When you use an advanced custom workflow like this, the final step is citing the tool accurately. You need to be able to translate all this complex technology into concise, rigorous methodological prose for your academic publications.
And the sources provide a very clear template that captures every single point of rigor we've just discussed. It's really the ultimate summary of all the system's benefits.
It starts by clearly stating the core model used, OpenAI's Whisper Large-V3.
Followed immediately by addressing the compliance concerns. So you confirm full GDPR compliance via local institutional HPC execution, and you emphasize the critical fact that no audio data or transcription content was transmitted to or processed by external third-party services. That is the necessary language for any ethics review board.
And then it meticulously details all of the custom processing stages that ensure the quality of the final output.
Right. So researchers have to cite the use of optional audio enhancement, noting its use of spectral noise reduction and dynamic range compression for improved signal quality. They have to cite the configurable language specification to prevent those erroneous language switches. And crucially, they have to cite the automatic detection and removal of those spurious text repetitions that are generated by the AI model.
And finally, the privacy measures, which are absolutely essential for defending the research ethics.
Yes, you have to specify the privacy protection through intelligent personal name masking, which replace detected names with anonymized placeholders, all while confirming the system's designed to avoid false positives on common conversational words. The template then concludes by referencing the full citation details, including the software version number, to ensure the method is completely auditable and reproducible for the long-term scientific record.
This whole deep dive has really shown that in this new age of generative AI, the path toward the cutting edge of data processing doesn't necessarily lead to the cloud. In fact, for sensitive, high stakes data, especially the kind of data we see in cognitive or social science, the opposite is true.
The core insight, really, is that the future of rigorous, ethical data processing relies on bringing these powerful AI tools back home, back to localized, controlled, and auditable environments. This is how institutions can successfully balance all this amazing technological power with the most stringent ethical compliance and methodological rigor.
The secure and scalable speech transcription workflow we've discussed today, which was developed by Dr. Pablo Bernabeu, is available under the Creative Commons Attribution 4.0 International License, which really underscores its commitment to open science and institutional adoption.
Which leaves us with our final provocative thought for you, the listener. This meticulously engineered offline workflow proves that the most powerful application of advanced AI models like Whisper isn't necessarily found in the most public-facing chatbot or API. Instead, it's in the quiet, rigorous, institutional implementation that prioritizes security and long-term scientific sustainability.
So the question for you is this.
What other cloud-first AI tools, whether they're large language models for analyzing medical notes or image recognition models for proprietary clinical data, what other tools need a similar local, secure reengineering effort to be truly trustworthy for high-stakes work in your field? That tension between convenience and control, that is the defining architectural question of our time.
Something profound to mull over as you plan the next methodological steps in your own research. Thank you so much for joining us for the deep dive.
We really hope this session provided the depth and the insights you needed to tackle the data sovereignty and transcription challenges that might be facing your institution. Until next time, keep exploring the source material.